Hi, welcome. In today's video, I'll be discussing about the general quantum states. I've been working on a quantum state which is in the SZ, SX, or SY basis. If we say that a quantum state given, for example, by ket psi is written in terms of A ket plus B ket minus, we say that this quantum state is in the basis of SZ, the operator or the observable SZ, and if we write this quantum state in terms of A ket plus subscript X, we say that this quantum state is written in the SX basis, and lastly, if this quantum state is written in terms of ket plus subscript y, ket minus subscript y, we say that this quantum state is written in the SY basis. Now, let's consider an operator A where its eigenstates are ket A1, ket A2, and ket A3. And let's assume that these three quantum states form a basis of our system, which means that for every A subscript I, ket A subscript J, where it's equal to 0 for all I different of J, and it's equal to 1 for all I equal to J. A quantum state written in terms of the eigenstates of the operator A is said to be a general quantum state, since A can be anything. This general quantum state might be ket psi being ket A1 minus 2 ket A2 plus 5 ket A3, for example. Well, let's exercise a little bit and write the ket psi in the matrix notation. Well, to write this quantum state in matrix notation, first, what would be the matrix notation for the ket A1, ket A2, and ket A3? So, an obvious way to do this, since they form the basis of our system, we can represent ket A1 by this matrix 1, 0, 0. The difference now is as our basis is formed by 3 kets, it means that each ket must have 3 entries when it comes to matrix notation. So here is the representation for the ket A1. For the ket A2, we could write this as 0, 1, 0, and the ket A3 we can represent by this matrix. As you can see, both these 3 matrices are normalized, and if we perform the inner product between one and the other, we will satisfy these relationships written here. Before I write ket psi in matrix notation, I'll normalize it first. I'll put it faster since you already know how to do it. This is our quantum state normalized, And now we are ready to find its matrix representation. As we discussed before, the matrix representation can be calculated by writing down the quantum state. To make it easier, we just need to calculate these three inner products to be the entries of our matrix. This is a basic calculation. I'll skip some steps, but I strongly encourage you, if you have any doubt, to do all the steps by your own. I'll put here 1 over square root of 30 in evidence, since all the terms here are followed by 1 over square root of 30. For the first inner product, we have 1, for the second -2, and for the third one 5. Then here we have the matrix notation for our quantum state ket psi. We can also calculate the probabilities of all possible measurement results of the observable A, and this probability, as calculated before, is given by probability of finding ket A1 is given by this expression. Probability of find A2. We already have all the results for the calculations. Value of these inner products here have already been calculated, as shown here, by the entries of this matrix, of course taking account this term here outside. Therefore, the probability of find A1 is 1 over 30. The probability of find A2 is 4 over 30, and the probability of find A3 is 25 over 30. As said before, the higher the coefficient that comes with the ket, the greater the probability of find that ket. As you can see through this example, the higher coefficient between A1, A2, and ket A3 is the coefficient that comes together with the ket A3. Therefore, the higher probability is for this ket as well, as you can see here through this result. I did all the calculations for the probabilities directly, but of course you can still find it through the matrix notation. I'll do it like in a faster way, just to show it how you could do that. To finish this video, let's suppose a different experiment where the system is prepared to be in the state ket psi prime 2A1 plus 3I ket A2. So from here we can normalize this quantum state. If you do it by your own, you will see that this quantum state normalized is given by this expression here. Also, we can represent this quantum state in matrix notation. If we do by ourselves, following all the steps I did before, you will end up with this matrix notation for this ket. The probabilities of finding ket A1 is 4 over 13. The probability of finding A2 is 9 over 13, and the probability of finding A3 is 0. Since the state ket A3 doesn't exist on the prepared experiment. You can check these results via matrix notation as exercise. It's worth mentioning, if the higher the coefficient, the greater the probability of finding that ket that is followed by the coefficient. Then, if the coefficient tends to 0, the probability tends to 0 either. In our case, we can interpret the quantum state as ket psi prime equals 2a1 plus 3i a2 plus 0a3. Therefore, if the coefficient is 0, there is 0 chance to find the ket that comes with it. In this case, ket A3. Thanks for watching. Bye-bye.